Okay, great. Then it's my honor to introduce today Daniel and maybe also Everett, who are going to talk from Runtime Verification, who are going to talk to us about KMIR and what they've been doing with the K framework and Rust. Take it away.
Wonderful. Thank you very much. It's wonderful to be here. Everett and I will go through KMIR. Let me share screen. I think I'll be doing most of the talking. However, it's always good to have a co-pilot and backup. So thankfully, Everett is with me. So feel free to jump in, Everett. And if people have questions, I really don't mind being interrupted. It would probably be better to resolve something confusing sooner than later. Let me try to remember how to use everything. I think I go, yep. So the topic of the talk is KMIR, and what I hope to do, I think on the short end, I'll run for 30 minutes, on the long end, maybe 45 minutes. We'll see. And I want to go over what is K, because if KMIR is the encoding of the operational semantics of MIR or stable MIR in K, there will need to be some understanding of the background here. And then in particular, what about what have we experienced by undertaking KMIR? So design decisions and our translation of MIR to K, our proof harnesses and specifications, and the challenges that we've overcome. After that, I'll talk about where we're currently up to and what we can see moving forward. This talk is pretty similar to the one from Rust Verify with some changes and additions because we've moved forward a bit. But if you were present for that one, it will run quite similar. So I want to do a motivating demo, or at least just show the interface for the tool as it currently is today. And so this is a checkout for MIR Semantics repository that is available at the Runtime Verification GitHub. And there's a couple of motivating, really simple arithmetic tests here. So one is simply checking that if we have a sum result for checked add, that if we did unchecked add, that we would get the same thing. And we would expect this to pass for any inputs that we provided here. And if we provide any inputs for this should fail, or not any inputs, but we would expect that we can find some inputs for this should fail, such that if we called unchecked add, this would be different from wrapping add because of undefined behavior. Now, KMIR, the interface works pretty simply. You do a KMIR prove, you point it at the file, and you select a directory to store. I might actually, I think I ran this before just to make sure it would actually run, so I might clear that out. But you provide a proof directory. This is where the artifacts will be stored. And you select a start symbol. So selecting the start symbol is pointing at which harness here or which proof you would like to run, and it will instantiate symbolically the arguments that are provided to that function where it can. Sometimes that's tricky, as I'll get into. So the start symbol, I guess I'll run. The interesting one would be should fail, so I'll run that because it will have a failing node, and I'll tell it to just, this is some internal stuff, terminate on thunk, just so it, when it runs into an error, it just stops immediately. It's kind of like fast fail. And I'll do it verbosely so we can see the output. So what happens with this tool when it starts running a proof is there are K definitions that are encoding MIR already. So this is the understanding of the operational semantics of MIR that we have currently got to. And it's compiling down to this particular program to MIR and extracting that as JSON, which then also gets parsed into MIR, and with the specification and the implementation. So the specification in this case is just we don't want to hit. Oops, we did this proof. We don't want to hit and assert. We want this to end gracefully. So it is compiling these definitions. This output is quite hard to read. I think Everett and I would be able to make sense of it quite quickly, but for a first time, it will be hard. But it's creating some definitions, which are the back ends, which it needs for proving. And once it's completed making those, it will start an RPC server, which I don't quite see right now, but I'm sure it's there. Here it is making directories to store the proof artifacts, and here it is starting the RPC server. And so this RPC server allows the prover to talk to whichever backend is best for the proof at the time. And this is the actual proof being executed. So it goes through, it runs the proof, and of course it fails. At that point, we could have a look what's inside. We could do a KMIR show of unchecked add, and we need to mention, we want to say, now that we've run unchecked add in this proof, it isn't unchecked add.rs. We want to go unchecked add.should fail. So the name of the proof that we ran should fail, and we tell it where did we store our artifact. So proof dir is equal to proofs. I might pipe that into less. So this gives us a graph where we can see an initial state, and then we take 53 steps in this proof. We get to this state where we're trying to do a binary operation here. We're trying to apply binop for binop add unchecked to some integers. And at that point, we split. So the graph splits here. And on one path, things end up working out. We get to our final end program state here, which is a happy termination. And down on this path here, we're stuck at a thunk. And so it's not easy to see if depending on the resolution that's coming through over the video call, but this is the dotted line here, which is saying that the target state was subsumed into this leaf node, and here it could not do so. It got stuck and was unable to continue with the proof. We also have a viewer, which is sometimes preferable. So this was a static view of the proof, but we can have a more interactive view where we can click on these terms and see the actual internal state, which at the moment won't be too interesting, so I'll hide it. But we can go through and look at the path condition. So this is showing the constraints. I can go through and see that on this path, there's a constraint that says that this will be A and B, so argument 1 and 2. This is just their internal representation name. If added together with integer, added together as integers, and so this is not capped, this is, mathematically speaking, if that is equal to the truncation of those two integers added together at 32 bits signed, then we're on this path. And that makes sense for the proof that we're in. So if we were never going to wrap, we would expect the results of these would be the same. However, on this other path, that same condition is false, and the rules of the semantics don't know how to make progress, and so they get stuck, and we can see that the proof didn't go through. So that's just a mild orientation for what does it look like to actually use the tool. That's frozen. Okay, I guess we'll see.
Sorry to interrupt, Daniel. Did you see the question from Opal in the chat a minute ago?
I did not.
I'm also only saw it just now, so I'm not entirely sure what this was in context to. But
I tried to respond to the question, but I don't know if my comments are being eaten or something. But the two backend,
I didn't see it.
Okay.
I can't. Maybe, are you sure you have it set to everyone in the chat?
It's
Everett?
set to everyone, yeah, which is confusing me. Do I need a permissions or anything? I mean, it says that
What are the
well,
backends?
Yeah.
Anyway, I should read out the question because it doesn't show up in the recording later. So the question was, why do you need true equals X? Isn't it sufficient to just assert X as a Boolean expression?
Yeah, that it would be, that would be an optimization. There's a lot of stuff that is still verbose or over explaining. So that is
so what is showing in there is the constraints, which are matching logic constraints, not Boolean predicates. And I think Daniel will talk about matching logic a little bit later, but in short, like Boolean predicate wouldn't be the correct type of formula to put in that. This isn't a Boolean and, this sharp and, that's a matching logic and, which is more like a set intersection for elements in the model rather than like a Boolean conjunction or something. And so true equals this is actually, true equals that is, the set of elements that are true in the model of bool. So it effectively just means the Boolean conditions that's on the right-hand side of the equals, but for it to fit in the rest of the formula, which also includes a bit of state, a bit of configuration state, which we can talk about later, you have to have it in this matching logic formula format. So this is just the way to make it compatible with the format that it needs to be in, basically.
All right, great.
Well.
I think that settles it for Opal, and I think we'll get to it later.
And then the other question, what are the backends that are available? There's two backends, the LVM backend, the Haskell backend. We're using the Haskell backend here because of because we want symbolic execution. The LVM backend is for concrete execution, and that generates an LVM interpreter for the language, and it's a pretty quick interpreter. So we're able to use it for doing testing and also use it for doing fuzzing campaigns and stuff. And to quantify pretty quick, there are several VMs that we have semantics for where our generated interpreter is as fast as a handwritten interpreter in an interpreted language, like in Python, rather than in C. In C, it's still usually faster to handwrite it.
The only other thing I'll mention on that is there is some amount of configuration as well that you can do to show or hide input. We can choose to pretty print the output here as we see fit, or for what's more intuitive for us to read when we're inspecting proof state. But going back over to the slide, so that was intended to just be a bit of a flavor for what we're talking about as we start talking about it. Now, with the demo out of the way, we'll talk about the K framework, because this is the thing that's underlying what's going on. So if we think of this as a visual representation of the K stack, so notice this internal core here of matching logic, which all of the things on the outside must be built on top of. So K is built on top of the matching logic, and this is the framework which we encode our operational semantics in. The backends are doing implementing the mathematical underpinning of that. And then we encode particular semantics. So this is one for EVM, this is one for WASM, more, and then we can build tools on top of those semantics, which we have them for software quality assurance. So matching logic is the core. We build K on top of that to encode the operational semantics, and that gives us access to being able to encode our particular languages. We want to be able to have tooling for Rust in the K ecosystem, so we have chosen to encode stable MIR, and then that will allow us to build whatever we need on top of that for the particular use case. So what is matching logic? There's a full description that you can find at matchinglogic.org, or you can follow this QR code. This is going to be just a super brief touch onto it. But essentially, if you consider that you can fix a model that is a universe of elements, where for an example, we have down here that the model is restricted to 1, 2, or 3, 4. and you have interpretations for symbols. So in this model, there are symbols even and prime. So even would restrict the set to 2 and 4, and prime would restrict it to 2 and 3. Then we can consider a pattern, which is then matching some subset within that universe. So what is within this, I guess, capture here, phi would be the matching symbol on M. So this yields a set of elements, not a Boolean result. So when we say something matches, it's not a Boolean, yes, it matches, no, it doesn't match, which I think is kind of matching up with what Everett said before. So just to do a super contrived, super simplified example, but if we consider, okay, within the model M here, if we have even and prime, well, that would resolve to 2. And not even within this model here would be 3 and 4. So that's like a really dumbed down version, and there's a lot more going on, but essentially we have these ability to match these sets.
Yeah, and for those who want a deep dive in matching logic, that website is a good resource, but I'll say it's just a small extension on first order logic. It is higher order, and allows us to define temporal properties directly in matching logic, basically, and then a few key properties about matching logic for people who like studying that logic and model theories. Things like equality and unification and matching are definable in the logic, as opposed to being something that has to be defined external to the logic and used to define symbols in the logic. So that's kind of a nice property for being able to emit proof objects for doing execution, for doing like program execution using our small step operational semantics, which we are able to emit proof objects for our LLVM backend, our concrete execution, which gives us kind of a transcript of the matching logic deductions that show you that, oh, from this input program state, executing this program, you get to this output program state or this output from the program, which has other use cases like feeding into zero knowledge circuits and stuff like that. So for people who are interested, I'd recommend checking out that website.
Awesome. With that rough idea of what's going on with matching logic and pattern matching, we can consider that this allows us to have nice ability to do rewrites. So once again, things are super simplified here, but if we consider that we have some context and in there we have Boolean true and false, well, if we have sufficient understandings of Boolean within here, we could always rewrite that to false, because anything and false is false. And when we have symbolic input where we have true and a B, and this B is not specified, or it's a free variable, I guess, at this stage, it's not constrained. Well, that would mean for rewriting or matching this expression and rewriting it, that we would have to split. So there would be considered the same context, but with the path condition that B was false, that would rewrite to false. And with the path condition that B was true, that would be true. And with Booleans, that would be a totality on the branching that is possible. With a notion of something like this, you can consider that we might have the ability to do a reachability claim, something to the effect of, if given a context that has true and some B, does that always rewrite to true? Would we get unification on all paths? And in this case, this would be false, because there exists a path, this one up here, where B is false because B is false, and that results in a leaf state false, which can never unify with true, which is meaning that it is not always reachable from here to get to true. Everett, I feel like you might want to jump in on something I say there. All good?
I know, all good, thanks. Sweet.
So this is as I said, this is the mathematical underpinning of K, and this is why I'm going over it. It's quite hand wavy at this point, but this just gives you a notion. As Everett mentioned earlier, this concrete execution, we implement this in our LLVM backend, and the branching the branching or working with symbolic input is what I mean to say. This is implemented in the Haskell backend. Now, it turns out that the most efficient way to run a proof that has symbolic input is not always to run with this backend. And so we have we use some combination of these where when we can, we run the LLVM backend, because it's not always the case that just because there is some symbolic information within a proof that everything needs to be represented symbolically. There's still tons of concrete rewrite steps that would happen in there. And so this is far more performant. Whoops. So that's sort of the underpinnings of K, and we implement that in those backends. I said the LLVM one and the Haskell one. And now K is the framework that we want to use to encode operational semantics of languages. So when we think about what we're going to need for operational semantics of languages, we're going to need some kind of state that is going to be manipulated. We're going to need a syntax of productions that are valid in this language. And then we're going to need semantics. So when we see them, when we go to process them, how do we manipulate that state and how do we progress forward? So this is what we have within .k files. So we define some config.k, which allows us to encode some program state in XML-like style cells. So we can store the current continuation of the program that we're interpreting symbolically or concretely. And we would be able to store whatever other state we needed. So here, for example, in the MIR world, that would be things like locals and stack frames. We also need to have syntax. So the syntax of MIR needs to be encoded in K somewhere. And so we have BNF style declarations, so very similar to encoding any other grammar, where there's syntax, here local. A local is a local, I guess, well, I want to say terminal, but with the identifier of the local. There's a local index. So with the syntax available, we need some semantics when we encounter these, what's going to happen. So rules.k, for example, would be where we write the semantic rules to transform that state. So here, if we see on the current continuation, the K cell, if we see set local at index 0 for 42, and then there's more on the concurrent continuation, that we would just call that rest. But if we see this at the top of it, well, then we know that we can take this off the top. We rewrite, this is a rewrite arrow, the rest of the K cell to being the rest. But we do this update here where local 0 is rewritten to 42. And so this is the way that we, this is a snapshot, but this is how we decode reading the transformations of these configurations. So all of that together gives us something like this. So these are snippets of the K side of KMIR. Of course, there's actually a whole bunch of files which encode this, but this is a snapshot of the KMIR cell. So there's the K cell that has the current continuation, the actual program that we wish to do in interpretation, that we wish to interpret. There's the return value of the program. It starts off with no return. We need the current function, the current frame that we're inside of, which will have the caller, the destination of where to go next. It will have its locals listed out. It will have a stack and memory and all these things further on. And we define the syntax. So def IDs, all of these are just your typical MIR constructs that you see. So whether or not you're mutable, operands, locals, basic blocks. And then we encode the rules for what to do when we see them. So feel free to ask questions. I think that this stuff should be pretty similar for people who have worked with doing formal methods with MIR before. So with an understanding of that, let's have a look at KMIR and what did we seek to achieve by doing this, and what are the challenges that we overcame. So maybe first I did have a demo. I need to remember the context for why I had that. I wanted to show that inside the actual file the configuration if anyone was interested in that. So this is the actual configuration of KMIR. So there's a little more there than what was in that slide. And these files here on the left-hand side, so inside runtime here, there's a bunch of MD files. And on the outside here, there's a bunch of MD files. Now, these MD files on the outside here, for the most part, not perfectly accurately, but we have had to change some things. But these are meant to be mirrors of what exists in stable MIR JSON at the time that we encoded it, or public MIR. So there was at the time that we did this an abi.md, and we followed that verbatim to essentially, but K style, to lay out the syntax. There was a body.md and things like mono.md and tie.md. And so these files here are trying to be faithful reconstructions of what was in stable MIR. And then where we get into the hairy details is at runtime, we need to figure out when we see these things, how do we actually process them? And so inside data.md, for example, we have this, it's a bit of a monolith file at this time, but this is where we actually write our K rules, which are processing that information. So I just wanted to connect the stuff from the slides down to this world, although I know that this would not be parsable to anyone that was unfamiliar at the moment. These are written inside MD files because we have the ability to write this K specifier here, and it means that we can write, the goal is to be able to write out operational semantics in a way that is useful as a semantics and is useful on the operational side. So we want to be able to have the documentation and the explanation of what's going on inside the file itself. So so here we see the documentation. There's a heading for copying and moving alongside the K rules that we have. Now that is also, so those configurations, when we were looking back here, these were the terms that we saw get output when we were looking at the different proof states. So with that in mind, the path condition down here and these configurations, this gives us a lot of inspectability into the proofs as we go through. We can choose where we want to break any of these states, and all of these proofs get stored on disk, and we can prune nodes and choose the granularity of how much we wish for them to be output. And I think this is like the core feature or the thing that makes having this particular prover stand out is the ability to have inspectability into these intermediate states at any branch, or we can put a request, we can encode what types of nodes we want the state dumped for, which I think is quite nice. Okay, so going back here, so with KMIR, what were our initial design decisions? So when we wanted to undertake this, so the first question that we had to ask ourselves was, were we going to encode the semantics of MIR, or were we going to encode the semantics of stable MIR, or I believe called public MIR now? So at the time, there was already a lot of tools that had done work with internal MIR or normal MIR, and nearly everyone was built on top of that. And we were pretty close to the starting of or just after the start of the work group for stable MIR. And it really seemed there was only Carney that was working with that at the point. And it made sense that we thought to target this intended third-party endpoint. So we've encoded that way. And the next question we had was, do we model the low-level bytes or the high-level data, or do we try to have some combination of the two of them? So when we're compiling down and we wish to extract this information, it could be pre-monomorphized or post-monomorphized as well. And we wanted to work with high-level data that is monomorphized. However, that means that we had a problem where we had to figure out how to deal with constants and allocations, because the monomorphization step there is important, or it affects things, which I'll get into later. So the next thing that we needed to make a design decision for was how are we going to extract stable MIR. At this point, there was a pretty printer for stable MIR, and you could write a tool in Rust to directly connect and extract from the typing context stable MIR, but there was no portable format. So all of our tools in the K ecosystem were pretty much built up to ingest JSON. We had this shared Python library to help orchestrate all of the things in the K world. And it really would have meant that we had less repeated effort if we could just get things into a JSON format. So we made this serializer stable MIR JSON to go through and just serialize all of those particular items that we needed. The next question is, how were we going to specify a Rust program? So this was largely influenced from things that were true at the time, which I'm not so sure are true now. At the time when we were doing this, we really wanted this to be a tool that would work for developers who were not necessarily familiar with formal methods. And what that meant is we wanted to reduce the friction of specification languages and DSLs that realistically we know that a regular engineer is probably unlikely to sit down and learn. So specifying inside Rust using macros was something that we wanted, and we wanted our harnesses to be like property test like harnesses. Now, come modern times with generative AI, there is definitely a question for, are people reading specifications and code at all? Like what are people reading now, and what is being purely read by tool output? But that was the design decision that happened at the time, at least. So with everything that I've just said, I want to give a bit of an architecture overview. So here is the Rust compiler. This is the input to the Rust compiler. This is the intermediate representations. We see the AST, the here, the there, the mir, and then code generation. But you'll notice the code generation is blacked out or grayed out because for running KMIR, we want to use stable MIR JSON, which is a Rust compiler driver, which is going to interrupt at the after analysis callback and do the processing that we need to serialize the data. So we have the target here. This is the verification target, the thing that we're trying to run a proof for. So this would include the specification as the property test like proof harness, plus have the implementation in there. And this would get compiled down. Things would get interrupted at that extraction point that I mentioned before. And then over here at this after analysis callback, this is a little outdated. I think this is called public MIR bridge now, and this is called public MIR. At the time it was SMIR stable MIR. This information would then through stable MIR JSON get, well, first of all, we call the collector and petition mono items as how we do the monomorphization. And then from there, we do the Serde serialization and get everything into our JSON. That is ingested by a parser that we have in Python. We have this repeated across many K semantics. So this is a reduced effort. This is largely similar to what we have in other semantics. And so it was able to take this JSON in, and this would provide us with a KMIR K AST. So this is the K version of the program here that we wish to run. But we also have in the KMIR world that we have encoded the operational semantics of K. So all of those files that I showed where I was like, these are the stable MIR JSON. Sorry, the operational semantics of MIR in K. These are the stable MIR MD files, and here are the rules to run them. So all of that information plus the program, the verification target, we can do concrete and symbolic execution with, and this is where we get our result reported as down. This is the final state here. Or of course, you iterate and you keep proving. But that's the overview of the architecture. Now, the first step is the stable MIR JSON. So to give you an idea of what that looks like, it is really just a big struct that is going to be serialized into JSON, and it has all of the information that we feel like we need, at least for doing KMIR. And even there's some stuff in there that we thought, why not serialize it anyway? We don't have to parse it in, and there's a chance that someone else in the world might find this interesting. But we track the information about the particular crate that we're in, and then we have the allocations, the functions, the ties, the spans, all of this information, the information about the machine. And this is done in a 3-phase pipeline. So we go through, collect the items, and then we have a bunch of visitors that go through, and after calling collect and petition mono items, on them, we go through and make sure that we massage everything into the format that we need. So that's what stable MIR JSON does. And to give you an idea of what these property tests like harnesses look like, this is an example from some production code. We proved the equivalence of two implementations of the Solana token program. And here we have in blue, this would be where we assert the precondition. So we have this cheat code here, cheat code account, which this will set up within our K configuration. This will set up the symbolic account there. And why I say that is because this is going to be tricky. So for our precondition here, remember what I guess go back to the example and remember what I said before. When we're choosing a start symbol, we could point it at this harness here. Now it should symbolically instantiate these arguments. However, this slice here that has an account info, or not slice, it's an array. It's a borrow of an array. But this account info is a raw pointer to an account. So this is a bit tricky to set up automatically. And so we ended up having a solution that was particular to this that we wanted to keep outside from generic KMIR until we feel like we got things right for a generalized setting. And so this cheat code account here sets up that symbolic data. The implementation here is what is called in yellow. And of course, the post conditions here are in blue, and they're a set of if-else statements with some asserts. So this is pretty similar to a property test. Okay, so what challenges have we run into along the way? I just want to see how I'm doing for time. Okay. So the challenges that we've run into in undertaking this, the first thing is we had to decide what to do with constants. So constants as bytes. So we had two goals, and they were in tension. We wanted high-level structured data, so no bytes in our value sort, and we wanted monomorphized stable MIR. So I have here that this is a K restriction. I don't actually believe it's like an explicit K restriction. However, at the time, we felt that it would be easier for us to do this if we had monomorphized items. So monomorphizing also evaluates the constants into bytes. And so this is just part of how the compiler works to do things. Now, the solutions that we had were we could do custom monomorphization, which I believe is what Charon and the other tools do, is choosing if you want to monomorphize, how to do it, not through calling collect and petition mono items and going through the main compiler toolchain, but doing your own version of it. And if anyone's here from these tools and I misunderstood, please correct me. The other option would be just to commit to the bytes. And we see tools like Carney or things that are going to do bit level model checking and things like this. Now, we didn't want to do that. We did want to monomorphize all the way down, but we didn't want to deal with the bytes. So what that means is we decode back up. And so there's actually another project that does this, but they do it not for stable MIR, but for MIR. This is SAW Crux MIR. We did a similar thing, and it means you have to build decoders for each of the types. Nice. I see that you say, Xavier, that for Crusoe, you do symbolic monomorphization, and Opal, Charon keeps track of the generics for the item and the items with generics substituted on demand, partly because Charon allows starting translation from anywhere and stopping anywhere with opaque items, so you can't just collect all items. Yeah, that makes sense. I think this is a powerful way to go. So we at least, we're decoding back up, and I'll move on to the second challenge. So casting and projection. So we wanted to, as I mentioned when I showed all of the files on the left-hand side there, these were faithful reconstructions of the stable MIR at that time. And when we were making the value sort, we decided that we wanted to make that as close as we could match the type, I guess. We wanted things to be as faithful as possible. And we knew that we were probably along the way going to learn that we would need to make some simplifications, but we wanted to at least start from this place. So this ends up getting quite verbose. So here there's some example where we have an inner is a wrapper over this U8 array of size 2. And then there's another wrapper called outer over that inner. And the array value for us is just a range that has these particular values for this example, 11 and 22. But then the outer value ends up being quite frustrating. There's an aggregate with a variant index of 0 that then has an aggregate with a variant index of 0. So this is saying that it's a struct on a struct, and then inside we have our range. And this is an example to have that fits on this slide, but I think you could imagine that this, without having explicit types, a lot of things, aggregates are enums, aggregates are structs, aggregates are unions. This ends up where you're just seeing tons of aggregate everywhere, and it gets quite confusing. So at this, so the problem is the verbosity in reading the values when we're looking at the tool output. And so some possible solutions that we have is just to keep with things faithfully and live with the verbosity. This sounds like a really bad idea, and we definitely weren't wanting to do this. However, it doesn't sound so insane in a world now where people aren't really reading things anyway. Although still, this is not the, I think, the long-term solution. But this is mostly what we've done up until this point. However, we have done some experiments with doing some pretty printing, but keeping the internal version as this verbose output, but pretty printing it when we're showing it to ourselves. But the other option is just to change what the value sorts are to be something easier to work with. And we have actually done that for some things, and it was nice. So another problem that we had when we did this was there was a ton of intern data that we were storing in the K configuration. Now, when we started to work with anything smaller than just example code, this blew up the size of these configurations and meant that when we were doing proofs, we were writing massive amounts of static data that was never actually going to change to disk. So things like the allocations, the ties, the functions, the spans, all of this information when we're doing a proof is just constantly being written there. Now, the concrete, so all of this information is concrete and static. So it gets very, very large, and we needed to reduce this in order to work with decent sized proofs. So what we did at first is we put everything into the LLVM definition, and then we had this extra compilation step where we would have to compile recompile the LLVM definition down to have this static information in there as well. As I mentioned, the LLVM backend is really, really fast. Evaluating these functions and doing a simple lookup for static information happens really fast in there. We did run into some problems where what this was doing was making it so that if we had tons of problems with extra compilation time when we had to do things like run the integration test suite. We've ended up doing a new solution to the problem where we changed the configuration, that configuration that I showed you in K, depending on how we're compiling and what we're doing. So If we're purely doing a run and we know that there's not going to be any symbolic execution in there, it's only going to be a concrete run, we add into these K cells all of that static information, because it turns out that we don't go and look at these anyway. They just run their course and we see what's at the end. Now, this is not true when we're looking at symbolic information. We're often having to look at many intermediate states and try and figure out what's going on in a proof. So symbolically, we can't have all that information there, plus it would have to be written to disk. And so in those cases, they get added to the Haskell definition, and by getting things just right, we can look things up without costing too much time in there. Maybe more to say on that in question time, but I'll just read out what Opal said. So not at all an AI expert, but limited experience is UX improvements for human users often benefits LLMs because it's easier to parse sentences for us and easier to read and consume less tokens for them. Some cool research to be done there. I suspect that that's the case too, Opal, that even so, it would be better just to have this cleaner. Moving on to challenge 4 with unsafe. So dealing with unsafe is a problem in itself. So how are we going to do it? What is our approach going to be? What we aim to do, the way that K works is you have a set of rules where if the conditions match, you rewrite over this arrow to the other condition. You rewrite what was here, or the cells, you rewrite the configuration so that it goes to the right-hand side of the rewrite. And you have restrictions on when that is when it is permissible to perform that rewrite. So you have to satisfy these side conditions. Now, this is fine for us when dealing with unsafe, as long as we can track down all of the times when it's permissible to perform the rewrite, that we respect the rules of unsafe. But that means that we have to figure out how to encode them. So sometimes this is easy and sometimes this is hard. But for something like different transmutes, you can see that it's largely mechanical how this would work. You just have to actually be able to encode it. Now, here we have this guard. So what is this K rule saying? This K rule is saying I want to apply a bin op. The bin op is offset. I have a pointer here. Our pointers carry this metadata, which tracks the current size of what you're looking at, the size of the origin that you're inside of, because you might be inside a larger collection, and your offset that you are inside that collection, so that you know that you're not going to overstep the bounds there. So here we want to perform an offset with this int that is size n. So that would mean increasing this offset by n, which is what we see on the right-hand side of this rewrite here. Now, the side condition that must be satisfied here, or the precondition that must be satisfied, sorry, is that this must be within the bounds of the origin. So we can encode the things with unsafe this way, but it is a large task to try and get all of them, I guess. So we have a limited coverage of this so far. Challenge 5. So this is the last one, and then I'll talk about future work and then questions. But we needed to be able to deal with multiple crates. So StableMIR JSON produces one StableMIR JSON artifact per crate. So what we ran into is how are we going to deal with cross-crate calls in that case when we're switching context. So there are a couple of options. You could choose to keep everything in these JSONs and load context in and out in K as you move between things. But we actually decided that what would be better, and it has been good so far, we haven't run into a problem with it yet, but is to, after compilation, join all of these artifacts together into one monolith JSON. And that way everything can resolve properly without us having to switch context. Now, there is a problem with this. All of the interned values, their IDs are respective to the crate. There's a solution. We have to just perform an offset with a high enough radix and go through, but this means that the identifier of the JSON is not the same as the identifiers in the linked JSON and monolithic JSON a change from those original ones. Okay, so where's the current status? So what we have at this point is an encoding of a subset of stable MIR in K. That subset is actually backdated to an older version of Rust. I am in the process of updating that currently to a recent version of Rust. And I've got through all the warts and issues of doing that, so that should be merged soon. We are able to perform concrete interpretation and symbolic execution on Rust programs. Those proofs look like property test-like proof harnesses with the specifications using a certain assume macros, and we have some extra cheat codes if we need to be able to inject things into the K state. And we're able to do verification of loops and iterators, although there's been some trouble there, but we're able to provide invariant lemmas in K for those loops. There's support for safe Rust and limited unsafe Rust. And we've used this to prove equivalence of two real-world Rust programs that are actually used in production. And these were Solana token implementations. So what are we doing looking forward? So we want to complete the semantics. What's left notably, well, there's some pointer intricacies that we have to deal out, but we haven't encoded heap memory yet. We have other semantics that have done so, but we just haven't got around to doing this yet. And then we need to work on optimization. We need to learn from the other production K semantics that we have. That's the nice thing about the outwardly growing ring of K is things that benefit the other semantics will benefit ours once we get our semantics finalized and in a mature state. Implementing, it would be nice to implement the aliasing model. So we had a conversation about this in the formal methods workgroup Zulip, and I think that K would be a excellent, due to its modular nature, I think it would be excellent to be able to swap in different aliasing models and analyze their effects. Now, we are looking for a new verification target or funding opportunities. If you're aware of any, please do reach out to us. I think that's everything, and I'm sorry if I went over time. Okay, I didn't go over time, but I've not left much. Sorry.
All right. Thanks a lot for the talk. And now, as usual, it's time for all of you to ask questions if there are. Someone's raising their hand. Opal, yes, go ahead.
I was just curious. You say you don't model the heap. Is that correct?
Yeah, not yet. We haven't.
But in that case, how do you handle references? Is it just because it's in the store, so it's easier to manage separately?
Yeah, so at this point, we never. So we have the static allocations available, and our references that we have must always come from a known location on the stack. So data that was already there, they are a stack depth and index of the local how far in they are at this point. Now, that's going to need to change, or it's going to need to be expanded, which is not that difficult to do with K. Once we have an idea of the heap, and we have already been discussing notions of global addresses at that point, or some ability to do global addresses.
Nice, thank you.
Yeah. Thank you.
Great. Next is Florian.
Yes, thanks for the talk. It's great to always hear news about KMIR. I was wondering, with your LLVM backend, do you think that it's possible that it could potentially in the future become like a competitor to MIR? Or do you think that it's out of scope and it's more like a nice thing to optimize your symbolic execution?
I think I'll let Everett take this, but one thing that I want to say beforehand is I would not think of what we were doing as being competition with MIR, but more so hoping to see that stable MIR and MIR would achieve the same results. So if we were to complete the semantics and notice that between the interpreters we saw some divergence, we would have to figure out why that happened. So that might be our implementation, or that we might be actually looking at something which shows that the public MIR and MIR have some divergence. But I'll let Everett say more, I think.
Yeah, I don't actually know what MIRI does, but I'll reflect what Danny said, which is basically, every time we've ever made an implementation of a VM or programming language, we've found divergences with other ones, and that's led to bugs being fixed across the board. So I think having multiple implementations that you're able to compare is always good. And yeah, I mean, what you get out of the LVM backend is, decently fast concrete execution. So if you can build, and it'll follow the same rules that symbolic execution does. So for example, if it hits some undefined behavior, or if it hits a, something that causes a panic, then you'll observe that behavior in the MIR semantics execution. So yeah, I mean, anything you can build as an analysis tool on top of that. What we've largely used the LVM backend for it so far, I guess, has been a handful of things. The first is just having a concrete execution engine backend that's orders of magnitude faster for doing conformance testing while we're building a semantics. And then the second is as a fuzz testing engine, as a quality assurance tool for developers. So the same property test that we feed the symbolic execution engine for verification, we also can just do fuzzing over using the LVM backend. And then we also have a debugger that's like a VS Code style debugger with like breakpoints you can set and stuff like that. And we use the LVM backend for that as well. So you can, kind of set a breakpoint in your Rust program and then, have it execute up to that breakpoint, then inspect all the state at that point and tell it like step over or step into types of. So we have that style debugger for any programming language basically that we have a semantics for. And there was one more. Oh, and then the final thing, I kind of hinted at it earlier, building proof objects of individual execution traces that then can be fed into a matching logic proof checker, which then, if you're familiar with what ZK circuits are, is turned into a ZK circuit. So then you can validate, pre-state, program, post-state correctness just by checking a zero knowledge proof certificate of a matching logic proof. So that's kind of a complicated use case, but it's something that's a little bit newer and is kind of interesting. So
That's nice. Sounds quite promising.
Thank you.
All
Hopes
right.
are high.
I have one more question. And it's like, I don't know. I don't know much about K framework. And maybe this is just something you decided to do a few years and run with it. But you generate these, like, as you said, very large tables that contain all the static information. Have you considered sort of compiling them into the K rules, if that makes sense? So that you have, like, instead of having a table with 10,000 functions, you have one K rule for each possible function call, perhaps.
Everett, help me out here.
Yeah.
Yeah, I was going to say that I think that is it.
Yeah. So there's trade-offs though. So that having the one, so we initially started with, having just the function table and the semantics. It led to having a huge semantic, a huge state, and that was just slow whenever we had to do any sort of disk IO, which for verification, we like to save the proof state to disk, not too infrequently. So then we had a second pathway, which basically would, put a new symbol in the functions table, which says, go look it up in the actual function. And then we compile into the K definition of function, which basically says like this integer goes to this function body or something like that. That was faster for small programs by a lot. But then we ran into a problem where K's pattern matching, once you get past like 1,000 elements, runs into like some sort of performance bottleneck issue. But it's not the runtime pattern matching, it's actually building the pattern matching tables at compile time. And note that when we're building the functions into the definition, we have to recompile the K definition. So that adds a step at runtime, which is a little bit expensive and annoying. But we found a way to optimize that step as well. But now we had to optimize the step of, okay, how do we make it so that the pattern matching definition building doesn't blow up? And so we had to do this thing where we say, okay, first stratify the function. So if there's 50,000 cases, break it into chunks that are 500 cases each. And if it's, we check the integer, is it less than this, but greater than this, then go to the sub function, So all that is fully built into the tool that Danny demoed today.
And we have got it to a point where before there was this massive problem, then we did this trade-off and this trade-off, and it feels like we've actually ironed things out where when I'm working with the proofs, I'm satisfied with the compile time, and things are running fine at runtime. So I haven't got any problem with it right now. It's working.
I see. That's interesting to hear. Yeah, I guess I don't know a lot about K, so it's not surprising that like whatever you do didn't just some another thing that gets slower.
Yeah.
All right. Are there more questions? Apparently, yes. Francisco, please.
Hi, hello. So can you hear me fine? Yeah.
Mm-hmm.
Yeah, I think so. So first of all, thanks for the talk. I just wanted to ask you if you think that if could KMIR actually be leveraged to do something like a live tool to try to validate the soundness of some MIR optimizations in the compiler? Or do you think there are any roadblocks that you may encounter?
I think that is a use case that could be possible. It's hard for me to forecast too far out, but as well, remember that we're not working with MIR directly, so we are going through stable MIR. Where I think I see the most value is not so much that this is going to unlock new features, but I see a ton of value even from this outset of being able to check, are we preserving the same behaviors across both ASTs? And I do think that there is a chance that we would be able to gain more information when working with things like MIR optimizations and inspecting intermediate states, like I said, of the configuration for what changes. Now, I say that without knowing the state-of-the-art tooling that is being worked with right now. So if this is like a domain that you're in, I might be thinking that there's a pain point that doesn't exist. But the capability to do it might be there. So go ahead.
We've definitely done this type of work before. So there was a paper which I tried putting in the chat again, but for some reason my messages just get eaten by that box and don't actually show up anywhere. But if you look up "Cut by Simulation" by Daejun Park, "Cut by Simulation" by Daejun, Daejun Park. There's a paper on the UIUC webpage called "Language Parametric Compiler Validation with Application to LVM." And as part of his thesis, I don't know if it actually got published somewhere or if it just ended up being in his thesis, but we have a semantics of LVM and a semantics of x86 in K, and this would basically validate the translation from LVM to x86 by taking execution paths in the LVM and mapping them to execution paths in the x86 and establishing that they were in a bisimulation relation with each other before and after each execution path. And you do the same with, we did a brief project with some folks at the Ethereum Foundation trying to validate that compiler optimizations in the Solidity compiler preserve semantics using basically the same approach, right? You have program before, program after. In this case, they're both in the same programming language instead of in different programming languages. And then you establish, some sort of equivalence relation between the states in the two different languages, or in this case, in the same language. Then you're just establishing which parts of the state you want to be equal. And then we do symbolic execution and show that that relation is basically preserved between the two programs. So I think it's definitely possible. It's not something where you like snap your fingers and get that out of the box with K, but with a appropriate pick harness, I don't think it's, it maybe be like a few weeks or a month of work or something pre-LLM. I don't know what it would be with LLMs.
So. Two months. I'm joking.
You're lucky.
Thanks.
Yeah, we have another
Okay.
project.
Sorry.
Yeah, go ahead.
No,
Sorry, just if this is interesting, we have another project where we took the semantics of EVM, which is KVM, and we have a lean 4 extractor for K definition. So anything that's a K definition, we can extract lean 4 code for. It's kind of an ugly, generated lean 4, but it's there. And so we extracted from KVM a lean 4 definition, and then we proved, again, using a simulation relation in lean 4, because the model we were comparing to wasn't as complete as KVM is, that all of the behaviors of the model in lean 4 were captured by KVM faithfully, basically. So that was a different approach to kind of so we could do something like that too, where you take like the original program, new program, extract the semantics to lean 4, and then just do the simulation proof in lean 4, for example. That's all.
Okay. I have a feeling that there are no more questions. Of course, if I'm wrong, please speak up. If not, then I think we should thank our speakers again.